Okay, the last time when we first started off on this chapter 5, the last time, right? We used to trigger activities. Without looking at the notes, can you recall what was the first one?
There's a trigger activity.
Trigger activities. There was actually the Tower of Hanoi, right? Then there was also the pizza cutting thingy, like you cut pizza into many pieces. And from the two trigger activities, we understood that those activities allow you to so-called model the problem using a recurrence relation. And in fact, we have learned how to solve them even. I remember that Vikram asked me for a proof of that belief. And I told him, don't have. And I was saying that Vikram will actually show the class the proof. Okay, that means Vikram didn't read the notes during holiday. It's actually the notes. It's actually the notes. I was just pulling a leg. It's actually the notes. I was trying to see who is the diligent one, Okay. Browse through. Right. It's okay. Alright, let us now look at the third trigger activity in the case of drug overdose. I want you to know that in the case of United States, you don't get to see doctors so freely or so easily like what we do in Singapore. In the US, if you have a cold or cough, they don't see doctors on. They sell Medicaid. They can go to the pharmacy and then buy medicine that's what they use. And the pharmacies, whom they I think they call them chemists, okay? They are allowed to prescribe stronger medication to you, right? I remember that I was once ill in the US, and you see, you have a cough, right? Cough in Singapore, right? You want to clinic to see a doctor, right? So easily, US not like that, I was in a hotel room, was so bad. They called a doctor in for cough and cold. You guess how much it cost me? $300 US.
Wow. So cheap.
Luckily, I can file for insurance claim. It's on personal trip.
How many years?
More than 10 years ago.
Okay, so that's like 600.
I also remember some doctors. I remember this particular doctor funny. He carried amoxicillin. There's a kind of antibiotic in his pocket. Just dig up from pocket. I had to take his medicine. So scary. He just dig up from the pocket. Just give to you like that. Anyway, so in this article, he says in the US, there's a misuse. There could be misuse of drugs, and then you end up with death or poisoning. Now, for a more well-defined question, let's look at this problem. Suppose you are put on a medication which is taken once a day. Each time there is 35 mg, and your body can burn away 70% of the drugs. Each time you burn away 70% of the drugs, 30% will stay. And then in your bloodstream, certain drugs cannot be in your bloodstream for very high level. Let me say you cannot have a very high level of certain drugs in your bloodstream, otherwise you can actually knock off or you can get into trouble, right? Especially if you take cough syrup, if you have a high dosage of cough syrup, it can make you high, okay. So now the question is, how do we formulate this problem mathematically, and how do we express the amount of drugs in your body system in terms of drug amount in your system the day before, So in this case, maybe let's define our xn, okay? Let's define xn as the drug you have amount of drug on day n, which means x1 represents the amount of drugs you have on day 1, and x2 will be the amount of drugs that you have on day 2. So if I may call this the amount of drugs you have on day 1, this on day 1. how much do you have on day 2? You can imagine that the amount of drugs you have on day 2 depends on what you have on day 1, and you cut off the amount that is being burned off, you left with only 30%, and then you add in another 35 mg. Right? This is what you're going to have after on day 2. Okay? Day 1, yes, x1 amount. On day 2, we have this amount. And then what you want to do is you want to formulate a recurrence relation of the form like this. On day n, the amount of drug you have is going to be 30% of what you have the day before plus 35 mg. So this becomes the recurrence relation that you intend to so-called solve. Right? This recurrent relation apparently models the scenario at hand, that the amount of drugs you have on day n is 30% of the amount you have the day before plus a 35 mg that you add in the day itself. Right? So now, do you remember how do we solve such a recurrence relation? The last time that we talked about, right? We talked about a certain belief. Remember? Okay, let us recall. Let's recall what did we do the last time, right? Supposedly we do it like this. If you have xn equals to 0.3 x of n minus 1 plus 35. Okay. How do we solve this recurrence relation? Do you remember? Okay, let's see again whether or not it talks about what you have at the start. So in this case, you're not told what you have at x1 day 1. We do not, so it doesn't matter. So let this one be an amount on day 1. Okay, amount on day 1, which we do not have in this case, not given in the question, but doesn't matter, right? Doesn't matter. So from here, let's learn how we can solve this recurrence relation. If you do it brute forcefully, you can create a number pattern. The x2 is equals to 0.30 x1 plus 35. What is x3? x3 is 0.30 30 square x1 plus 0.30 times 35 plus 35, and then x4 is going to be 0.30 power 3 x1 plus 0.30. If you do it by brute force, this is going to be the case, no? And then the last time we learned how we can deduce that, therefore in xn, on the day n, again on day n, this is the amount of drugs that you have in your body. But you can do it brute forcefully like this now. So then from here you can find xn as equals to 0.30 n minus 1 x1 plus the GP formula a into 1 minus 0.30. How many terms are there? N minus 1 terms over 0.7. Right? So from this expression, we will know that as n goes to infinity, xn in this case will go towards what? Will go towards 35 over 0.7. What is 35 over 0.7? 50, is it? Okay, thank you. Yeah, I think it's 50. Right. That tells me that after a long time, if you take this medication on a prolonged period, long enough, you find that at steady state, right, the amount of drugs in your body is 50. So based on the description of the question, if 54 is the damaging level, right? And then your calculation shows you that at steady state it is 50, this drug and the dosage per day is safe, right? So this one way we can go about solving the recurrence relation, and from there we can work out the limiting value of this recurrence relation, right? However, do you remember the belief method? Okay, if you do remember, I'd like you now to scroll down to example 7. There's a blank space there in example 7. If you just go down to example 7, there's a blank space there for you. Example 7. Okay, in example 7, right? In example 7, if you were to believe, remember, you believe if this is my recurrence relation based on our description, or based on our description, right? Okay, we believe that the solution of this recurrence relation is this pink color. Can you see on the screen? Okay, the color is not very good. Let me change a different color. Right. Okay, then we have to actually form simultaneous equation wherein we actually solve for your capital A and capital B. How do you form the simultaneous equation? We use the x1 condition. In this case, x1 is taken to be 35, which means you start off with a clean body. On day 1, you pump in 35 milligrams. Okay, so it's assumed. In the earlier discussion, they didn't say that. They didn't say that it start off with a clean body. It just said that every day you're given 35 mg. So now, reading here, we presume that on day 1, when you're given 35 mg, you're starting on a clean body that hasn't got the amount of drugs at all, right? So if x1 equals 35, we can form the first equation. Right, this is our first equation. Oops. This is our first equation. Okay. This is our first equation. We write now as first equation, equation 1. Yao Tia, how do you think you can form the second equation? We have to manually calculate our x2. How do you calculate x2 though? Because if you know x1 is 35, x2 is simply 0.3 of 35 plus 35. You know what I'm saying? And then you got your value of x2, and your x2 is equals to 45.5. And using this x2 value, I can now form a second simultaneous equation, or second equation for this. Okay, let me erase off and write that. Okay, this is the second equation. This one equals to 45.5. My second equation. It's already in the notes, okay? It's already in the notes. Right, I believe the notes already has it, right? Right, okay. So from these two, you can then solve them simultaneously for your A and B. And then this becomes your solution of the recurrence relation. From this recurrence relation, from the solution, we can actually find that when n goes to infinity, we can see from here now, when n goes to infinity, right? As n goes to infinity, right? As n goes to infinity, xn in this case goes towards 50. Right, again, it is a safe level. Right, so this is actually one way of solving the recurrence relation using the belief. Right, what is the belief? The belief is if your xn is always like that. Plus another number, okay? Plus a number, doesn't matter what number is. If your recurrent solution is like that, the belief is this will be the kind of solution you will have. It will always be like this. Just a belief. Are you clear? You are encouraged, yes.
Why do we believe?
Because the notes provides a proof for you. Okay, because the notes provide you with a proof that this is the case. Okay, so where is it in the notes right now? I'll bring you to it. I'll bring you to it very soon. Okay, very soon. Okay. There is a so-called method 2, no? There's actually a so-called method 2. This number that I call star is typically denoted as a letter B. There's a method 2, no? This method 2 is like learning math the bio way, you know. That if you have an equation that is like that, they're saying that this is a solution. And you just apply this thing, no? You just apply this thing. What is this thing? What is MSMD? What is MSMD? It is called monkey see, monkey do. Now, with this solution given to you in this manner, you just have to plug and play, you know. Okay, let me just illustrate to you that it works and it gets you the same answer as what we have in the green patch here. Okay. If your equation is of this form, okay, class, this is the solution. Again, it is built upon the belief. Not to worry, no. I'll bring you to it slowly, right? Thank you for asking, you know, why should we believe, right? We will come to the proof later on. But in the meantime, let's believe that this will be the plug and play solution. So let's plug and play again. According to the solution, this is going to be xn equals to, the a is 0.3, remember? 0.3 to the power of n minus 1 plus b is 35, and then this 0.3 n minus, okay, let me erase off this one first. Okay, let me write nicely.
What about the x1?
Oops, thank you for pointing out. X1 is 35 plus 35 0.3 n minus 1 by 0.3 minus 1. So now my job is to tidy up and demonstrate to you that these two solutions will match. Okay. Are you ready for this? Okay, so this will give me 0.3 n minus 1, 35 minus, okay, I believe it is it's recorded. Yeah. 7/10 is 50. Okay. And then there's going to be minus plus 50. Can? Okay. Then what's going to happen here is, okay, we are going to combine them together. Did I make any mistake in my math? Okay, it's going to be 0.3 to the power of n minus 1 minus 15, right? Then plus 50. Okay. I'm gonna have an issue now. Luckily, luckily, okay. 0.3 to the power of n. And in the end, you truly get minus 50, 0.3 to the power of n plus 50, which tallies with the earlier one. Okay, to be honest, I also find hard to memorize this bulky formula. I wouldn't do it myself, I wouldn't do it. I will use the other method, the method 1. Because to memorize the method 2 answer, like the formula, I find challenging. I myself won't be able to do it, to be honest. Unless I write down my palm first before I get an admission hall. Yeah. You just write with an invisible pen, then with a certain kind of glasses you can see inside the hall.
But you will never do that, right?
I don't dare. If you discredited all your years of achievements, we all go down the drain. Okay, anyway, I've demonstrated to you that I can get to the same answer. In fact,
You go to the toilet, no one can, and you're not going to check the inside of your pants for writing, right?
Why? Okay, Vikram, luckily there are no guys inside this classroom. I mean, no girls, I mean, yeah. Sorry, no guys. Yeah. Actually, it's quite nice to be in an all-boys environment. I grew up in an all-boys school. In an all-boys school, you can do a lot of things as all boys. Yeah. It's quite nice. Actually, it is highly unlikely that you and I will use method 2. It is more likely that you and I will just derive it on the spot. That means we will iterate a few terms and after apply the GP formula right on the spot to get the answer. It's more likely to be that way. Right? So-called, if I may call it, it may call it method 3. Okay? So up to here, right, we have covered 3 trigger activities. I have also demonstrated to you how we can solve them in the previous lesson and also today. And now to bridge the gap, we now want to go to this page. If you can go with me to this page, just go back 1 or 2 pages away. Here, okay. Here, it says 5.3.3. This is a page that wants to show you how you can solve them using so-called. This is so-called the method 2 using formulae. Right? This is the method 2. The method 1 was the belief. Remember? Okay, now let us now have an understanding of why this formulae work. And very soon you will realize that it's actually exactly the same thing we have talked about in the first lesson on this chapter and also today. What do you mean? So let's try again. Let's try. Okay. Let's do this one first. Let's do the case where A is 1. When A is 1, right? When A is 1, you will have a recurrence relation that looks like this. Sorry, the A is gone. If a recurrence relation look like this, right? What kind of recurrence relation is this called? It's an arithmetic progression. Remember, we talked about before. It's called an arithmetic progression. Okay? In the case of arithmetic progression, do you remember how to solve it? That the n term, right, is always equals to the first term plus the term number less 1 times the common difference. B in this case is the common difference. Right? Remember in the good old days, this number is called the common in the topic on APGP, this green color B used to be denoted as D, donkey, but now we use B. So if A is 1, it's done. It's just the arithmetic progression. Okay? So look at the recurrence relation. If it's of the type where the A is 1, it is simply a arithmetic progression and you're done. Okay? If it is not, if A is not 1, if A is not 1, right, then you write down x1 is x1, x2, right, x2 is equals to ax1 plus b, right? What is x3? Is a square x1 plus a b plus a, sorry, not plus a, plus b. Right, this is x3. How about x4? A cubed x1 plus a square b plus ab plus b. Then by so doing, you will eventually know that xn will look like this. Okay, and from here, what do? You will apply the GP formula for the behind terms. And the GP formula works because A is not 1. So that's why the GP formula works. If A is 1, then it won't work, you know. So that's how we get the proof for, okay. And do you know that this proof also allow us to actually prove that the belief is also true. The belief. Okay, how do you do it from here, no? Okay, from here, right? From here, if you do this, don't bring your eyes again. Don't bring your eyes. If you were to group this way, x1, are you okay? Right. If you look more carefully, one final line. So based on this, right? Based on this, you now come to this conclusion that the solution is always A. Can you see the big A? Big A, then 8 power n, and then to the big B. Can you see? The belief that we have that the solution is always A plus a B. Right, so that actually closes out the loop that Vikram raised the last time. Why should we believe what it is now? And now the conclusion is being established. Nice, right? So you can actually believe the pink color, or you can derive on the spot. You know what I mean? Or you can actually make use of the so-called formula. Seriously, it's quite challenging to try to remember this formula. Quite challenging. Yeah. I would rather use the belief. No, it's easier because they are solved simultaneously for A and B. Yes. Can go to it? Sure. Okay, let's read the remarks again. The remarks say if A is 1, remember when A is 1, I told you it's simply an AP. If A is not 1, I told you already, we are able to prove that this is always the solution, right? Our belief. Okay? So in the absence of the first term, you might not be able to find the capital A or capital B, or both, right? So just leave it as a general solution. If B is equals to 0, if B is equal to 0, right? If you look back, if B is equal to 0, if B is 0, right? If B were to be 0, in this recurrence relation, right? If your B is 0, what kind of recurrence or what kind of number pattern would you get if B is 0? If B is 0, right, the last remark that it says, if B is 0, what can you say about the recurrence relation? It is a GP. That means if B is 0. So if B is 0, you're trying to say it, then it's just a GP, then there's already a known formula for finding the nth term of a GP. Right. So this page closes up the loop, about what we talked about. And you'll find that again, after a little while, believe me, you will choose to believe. It's easier. Okay, you choose to believe. Right? So with this understanding, you now want to look at example 7. Example 6, right? Example 6. Okay, without even looking back into your notes, right? Let me ask the class, what is the recurrence formula for the Hanoi problem, Tower Hanoi? The xn is equals to
2xn minus 1.
right. This statement is true for, and then x1 is equals to what? 1. Okay. The last time we did it brute forcefully. Would you want to try to solve this using the belief? Can you try to solve this recurrence relation using the belief? Try. Try to solve example 6 using the belief. Sure. Vishal, what's going on? Justin, what's going on? Vishal, have you done my problem? You sure?
Yeah.
Okay. So you use a belief, right? You use a belief. You therefore start off by saying that xn is equals to a into 2 to the power of n plus b. So you form the first equation, a is equals to 1, equation 1. Then next one is a into 4 plus b is equals to 3, this is equation 2. Then you solve them simultaneously. You get A equals to 1 and B is equals to minus 1. Therefore, your reconciliation is 2 to the power of n minus 1. Which means if you have 5 disks, you will expect 31 steps. Right? If n is 5, oh sorry, do you say if there are 5 disks, right? If 5 disks, then you need 31 steps. This is to solve the Tower of Hanoi problem using the belief. You can also use the formula, no? It's already documented for you in the notes. So that covers, sure. That covers the example 6 and 7. And also the page before example 6. Okay, so now I'm going to roll back to example 1. You roll back to example 1. You find it very easily. Example 1. Okay. Example 1, right? Okay, I'm going to tell you more about example 1. Okay, for example 1, right? It just merely asks you for the recurrence relation, and we have discussed and we already understood this. And you do remember that example 1 actually goes along with example 7. And you do know that in example 7, I was able to show you how to solve it and then obtain the so-called the limiting value of xn. That means as n goes to infinity, what is the limit of xn? Class, let me ask you this question again. Looking at the yellow patch on the screen, let me ask you this question again. If I ask you the same question, this question, and I say to you, can you find this value without first solving the recurrence relation?
Yeah, very easy. I power equilibrium and then x equals x. And then solve.
Clever. And xn will equals to what?
Huh?
Xn will tend towards what?
50.
How do you get 50?
So x is x, right? If it doesn't change, then infinity. So 0.7x is equal to 35.
Okay, so class, actually, if you know that the recurrence relation converges, you can immediately write down the limit of the recurrence relation, or the limits of the sequence. Let me have a show of hands. Who do not know how I get this answer so quickly? Okay, let me show you why. Okay. To start with, do you agree with me that if the limit when n goes to infinity of xn, right? If this is L, do you agree with me that Wei what will this be equals to? Very good. So that being the case, I can say limit n goes to infinity of xn is goes to 0.3, limit n goes to infinity right now. Then this becomes what? This becomes right, and from which by L emerges as 35 over 0.7. Okay, right. So this is actually a way out to calculate limit without the solution. So if you have to answer this question now, will the amount of drug reach the critical level of 54 milligrams? Okay, you want to realize that in this case, right, in this particular example, xn is defined as the amount of drugs in the body after a new dose is given. You know what I mean? And based on our calculation, if at the steady state, right, at the steady state, xn reaches a steady state of 50, that tells me that okay, the amount of drugs in the body, right, no matter what n is, right, will always be lesser than 54 milligram, since xn, right, xn is equals to minus 50. We had this, right, 0.3, and just now with this fella, right? Remember our solution on this, right? This fella is always less than 50, you know, for all n. Therefore, is safe. Less than 54, sorry, less than 54. In fact, it's less than 50, okay? It's less than 50. Maybe I should be more precise, less than 50. Because we solved for xn just now, our xn was like this, right? And it's always less than 50 for all n, therefore we know that the drugs and the dosage given is safe.
This is a very dubious way of administering a drug. Like one day you accidentally take 40 and then you just die. Yeah, it happens. Like,
Self-destruction.
Usually the tolerances are far less tight than this. Yeah. It's usually not this.
Okay. Example 2. Okay, for example 2, right? For example 2, the reconciliation was this. Do you remember? Example 2. The example 2 pairs up with example 6, you know. Remember? And then we have learned that this thing turned out to be remember? We solved it just now. So with this, right, we can write down, they say, we can write down x1 to x6. For x1 is 1, 3, 7, 15, 31, 63, right? This rabbit thing is a little bit new already. Read the rabbit.
This is like 2 to the power 2 minus 1. Wait, no, 2 to the power n minus 1. Is it? What?
Example 3. Let's see who can formulate example 3.
Taking people like that.
Yes.
No.
For this one, right? For this one, I'd like you to do this now. N and xn. I'd like you to do this. Okay, let's try again.
Maybe the after last time goes on.
Okay, you start your first pair of rabbit right now. Okay, start first pair of rabbit. Okay, in the first month, right, you need one pair of rabbits. Okay, in the second month, how many rabbits do you have? Still one pair.
Depending on how you define
In the second month, right? In the second month, it's still one pair, no? Because the one pair you put in that you have in the first month does not produce anything. The second month, it is still one pair. This first pair that put in on the first month doesn't reproduce, so it's only one pair. After the second month, and now the third month, right? The third month, how many pair of rabbits do you think you have? You have the pair you have in the second month, plus that now it has grown 2 months old, it can produce another pair, so it becomes 2. So in the fourth month, right? In the fourth month, bearing in mind that the two rabbits, the two pairs on the third month now still live in the fourth month, assuming there are no death, okay? And then only rabbits that's 2 months old and above then can reproduce, right? How many rabbits will be reproduced? Only one pair, no? So that becomes 3. In the 5th month, you have the 3 pairs in the 4th month, and then there were 2 pairs by now who are already 2 months or more old. So the 2 pairs which is old enough will produce another 2 pairs, so you gotta get 5 pairs. And after a little while, you realize that this rabbit thing, right, it generates for you a number sequence known as the Fibonacci numbers. Fibonacci numbers. Yes. You read the literature of this. It started off with this, and then it developed into golden ratio and so on. You know. Okay, I cannot recall exactly. I think it's to take the limit of xn over xn minus 1. We try later. We try it again. We try the limit. Okay. Yeah. Is the limit of xn over xn minus 1, if I remember rightly. And you get general formula first, then you do the limit. Okay, so now we have the case of example 3. And now if I ask you to formulate the recurrence relation for example 3, what do you do? You will say the amount of rabbits you have on the n month is always equals to what you have the month before plus what you had. Right. Because the rabbits that you have 2 months or more before will produce additional so many rabbits. And now we want to solve this recurrence relation given that x1 is 1 and x2 is also 1. Okay, and it turns out that to solve this DE, it is not as easy as what we solve, the way we solve like the earlier ones. It's not so simple anymore. To solve this DE, right? To solve this DE, right? To solve this DE, it is no longer as simple as what you saw just now. Yes. Step 1. Step 1. You write down this equation, you know. Step 1. Step 1, okay, you write down this equation. And then you solve this equation. Okay? Step 1. So it's close to this. Both real, sorry, my bad. My silliness. Sorry. Right, my bad. Okay.
Oh my god.
And then from here, you form simultaneous equation. In A and B. Speak.
Where do you get this equation from?
I'll tell you shortly. If you do it correctly, right? You do it correctly.
It doesn't work. Prepare plus.
Right. So which means if you solve the Fibonacci pattern, right, the xn will turn out to be 1 over root 5, 1 plus root 5 over 2 to the power of n minus 1 over root 5 This is a solution for the Fibonacci number.
Yeah, okay, no. I do care about the book, not all. What's the just the larger.
That's the question, yeah, I prefer the first one. The second one, I ask you like why
Okay, now to unravel the mystery, you now want to first and foremost, okay, you try, you bring n as 1, you must get 1. You bring n as 2, you must truly get 1 still, right? You bring x as 3, you must get 2. And put n as 4, you must get 3. It may look impossible, but believe me, I've tried out before, no? I put in n as 1, it's true, it's 1. And put n as 2, it's still 1. When n is 3, it does give me 2. When n is 4, it does give me 3, and so on. I've tried before. Okay, so this is actually the solution of the Fibonacci numbers. Okay? Then now we have a question to answer. How do we know that the way to solve such an equation is what I just told you? To start off with, right? To start off with, class, you want to realize that this yellow patch equation is unlike the earlier ones that we saw. What is the difference? In the earlier one that we saw, your xn is only in terms of xn minus 1, don't have xn minus 2. I mean, the moment involve an xn minus 2, things becomes very different already. And to unravel all the mystery, you must actually look into page 13 of your notes. Now turn with me to page 13 of notes. You look with me to page 13 of notes. Page 13 of notes unravel for you the mystery surrounding all my beliefs. This page. My time is up to 12:30. Okay, I will not hold you any further. We will continue with this discussion next.